Hi everyone, in this lecture we are going to continue our discussions relating to constructing internal forces diagrams using the equations. And in here I'm going to discuss the second example in which we have a simply supported beam subjected to constantly distributed load. Okay, and in here before we start, I would like to call this joint over here is joint A and this joint is joint B, okay, where joint A is pin supported and joint B is roller supported, and then the uniformly distributed load is applied across the beam. Okay, from what we have learned in module 5, we know that the reaction forces here, AY and BY, right there should be W naught L over 2. Okay, so I encourage you to calculate this on your own and prove that you will obtain the same result. If not, then please let me know. Okay, and in these example problems, we need to construct the shear and the moment diagram. Okay, by first formulating the shear and moment equations. Okay, and let's say that we start our x. Okay, it's starting from A, going to the right to B. Okay, and then as what we have discussed in example 1, the first thing that we have to do is to figure out how many ranges is in this problem, in these structures. And these ranges is depends on the consistency of the structures in terms of whether there is applied loads or there's a reactional supports at a particular locations at that structures. And let's do this together. And we start from point A, okay, and then as we go across the beam to the right, we see that everything remains stay the same. Okay, remains stay the same until B. Okay, so everything's within this span. When we make a cut, it will give us the same cut whether it's left hand or right hand free body diagram. Okay, and then afterwards, it means that we can cut anywhere within this beam. Okay, within the span of the beam, and when we make that cut, it will expose us to the left hand free body diagram and then the right hand free body diagram, right? Okay, and we should also include the AY in here and BY, right? And we also have M of X, V of X, and N of X, but it's 0, so I'm not going to draw it. Same thing in here, we have M of X, V of X, and N of X, but N of X is 0, so I'm not going to draw it. Okay, and in here we have a distance right there is X. Okay, similar to what we have done in example 1, and the distance in here is L minus X because the total length of the beam is L. Okay, and similar to what we have learned in the previous examples, once we have this left hand free body diagrams and the right hand free body diagrams, okay, we can use it to construct our shear and moment equations. And in here I will just to show you the solutions using the left hand free body diagrams to construct the shear and moment equations. I will strongly encourage you to try verify the result that I obtained in here using the right hand free body diagrams. Okay, alright, and then let's use this left hand free body diagrams and let's do the calculation. And remember that in here when I draw the diagrams, okay, I include the distributed force as a distributed force instead of the resultant force. Okay, notice that how I draw the diagram in here, because many mistakes that I found from the students is that when they try to calculate this W naught L over 2, they try to simplify it into a single resultant R at the middle, right? Which is W naught times L, right? Then afterwards, they make a cut based on this load, okay, instead of using W naught, okay? That's wrong, okay? That's wrong when you try to calculate the internal force equations, okay? So do not try to simplify the distributed force, okay, when you make a cut in order to calculate the internal force equations, okay? But you can make the simplifications, okay, this resultant to calculate the reactional forces. That's totally fine, okay? And in fact, that's how you're going to do it, right? But for the internal force, you have to consider the load as a distributed load instead of a resultant force, okay? Then after you make the cut, right, obtaining the left-hand free body diagram and the right-hand free body diagram, right now you can make a simplifications of this the section of this distributed load, right? And we call it R prime instead of R to differentiate what we have written in here. So this R prime instead of W naught L is W naught X, which tells us is only the resultants of the section of the distributed load located at the distance X on the beam, okay? So once we already have that, we can do some of the forces in the Y. I will have AY, right, minus V of X, okay, and then minus R prime equal to 0. So my V of X is AY minus R prime, okay, and my AY is W naught L over 2, and my R prime is W naught X, okay, and this is basically my shear equation, right? And then I can calculate my sum of the moment at the point of the cut, right? Let's call that point 1. Sum of moment at 1 is equals to mx, right? And then minus ay times x, right? Because this is the distance, right? And then plus r prime times x over 2, because the distance over here is x over 2, right? And set this equal to 0, then I have my mx is equal to ayx minus r prime x over 2, ay is w naught L over 2 times x minus w naught x times x divided by 2, and I can further simplify this. I obtain w naught L over 2x minus w naught x squared divided by 2. Okay, alright. And then notice that one thing that I would like to mention in here is that when you take the derivative of the moment with respect to x, it turns out you will obtain w naught L over 2 minus w naught x. And guess what? This expression is exactly the same as the shear. Okay? And with that, I think we already formed the equations. Now we are going to plot the diagrams, okay? And in plotting the diagrams, I like to sketch the whole beam again, okay? And then this is the distributed load, W naught. And I also like to sketch the reactional forces on the beam, okay? And then afterwards, I'm ready to sketch the shear diagrams. And this is our X, right? And then this is L, right? And then this is our Y, which is V of X, right? And in here, the equations that we obtain is W naught L over 2 minus W naught X, which tells me when X equal to 0, I will have W naught L over 2 minus W naught times 0, so is equal to W naught L over 2, okay? And then at L equal to 2, right? At X equal to L over 2, right? I have W naught L over 2 minus W naught times L over 2, so it is 0, right? And then at V, at X equal to L, right? Then I will obtain it here if you perform the calculation, negative W naught L over 2. And it seems like in here, the line is a first order. So I'm going to sketch the shear diagrams as shown in here, where this is positive, this is negative, and the magnitude in here is W naught L over 2, here is negative W naught L over 2. Okay? And from the calculus, you may be able to relate that once you have, we show that in here, the shear, it turns out is the first derivative of the moment, right? And when shear is equal to 0, right? When the shear equation is equal to 0 in here, from the calculus, we learn that we will obtain a local maximum or local minimum, right? So in here we have a quadratic curve, a second order polynomial, right? And once we plot that curve, right, and we will obtain something that is a local maximum, because if you take further derivative, right, of the moment equations, you will obtain negative value, right, which tells us that we have a local maximum. Okay, so we have a local maximum when X equal to L over 2, right? And then we can calculate that by plug in X equal to L over 2 to the moment equations over here. We have W naught L over 2 times L over 2 minus W naught divided by 2 times L over 2 square, and if you perform this calculation, you will obtain 1/8 W naught L square. Okay, so the value right there is 1/8 W naught L square, and if I can draw the second order curve, it will look like. Alright, okay, and I think that's it for this problem. It's pretty simple, right? But however, I would like to end this lecture by asking you how many ranges are there in these structures. Okay. For example, I have a beam that is pin supported at A and roller supported at B. Then I have uniformly distributed force applied. Let's say that this is 3L over 4. The length here is L. Okay, and then we have a couple applied right there. Okay, at point C, located L over 4 to the right of point B, and a point load applied at the tip D right here. Okay, so for your exercise, how many ranges are there in these structures? Okay, and again, please remember that the way we figure out how many ranges are based on the consistency of the structures in terms of whether a reactional support or applied external load are exist in the structure or not. Okay. So with that, I think it's enough for this lecture. Please let me know if you have any questions. Okay, and thank you for listening.